To contain a star on Earth, the standard engineering approach relies on brute force. Classical tokamak reactors use massive electromagnets to crush superheated plasma inward, but this creates immense pressure, and inevitably, the turbulent plasma fractures the rigid boundary. Project Elyasia approaches this problem through a different architecture, the spheromac. Rather than fighting the plasma with applied external force, this design relies on the fluid's own ability to self-organize into stable topological shapes. This requires discarding a long-held view of the physical world. In James Clerk Maxwell's 19th century formulation of electromagnetism, the observable magnetic field, the B field, was considered fundamental, while underlying potentials were treated as mere mathematical conveniences. In 1959, physicists Yakir Aronoff and David Bohm proposed a deeper reality. They argued that the observable B field is actually a secondary effect, a ripple on the surface, and that the invisible magnetic vector potential, known as the A field, is the true fundamental architecture of the universe. This insight is the starting point for Project Elyasia. Targeting the underlying A field rather than overpowering magnetic forces opens a pathway toward a containment system that avoids the brute force collisions of classical physics. Proving the A field was a tangible object was a monumental challenge. Because classical physics dictated that a particle must experience a direct, localized force to change its state, researchers had to prove that a potential could physically alter an electron without the electron ever touching a magnetic field. This was achieved by Akira Tonomura. He fabricated a microscopic, donut-shaped magnet and completely encased it in superconducting niobium. Using the Meissner effect, the superconductor actively expelled all magnetic field lines, trapping them 100% inside the physical ring. Tonomura fired a split, coherent electron beam so that one half passed through the empty center hole of the magnet and the other passed around the outside. This ensured that neither beam ever made physical contact with the trapped magnetic field. When the beams recombined, the resulting interference pattern showed a dramatic pi phase shift. The only possible cause for this shift was the invisible A field lingering in the empty vacuum, physically altering the quantum state of the electrons. This definitive experiment proved that the A field is a tangible physical entity. It validates the core premise of Project Elyasia. Energy and information can be mathematically engineered and stored within the phase geometry of a field-free space. In an unconstrained environment, magnetic fields are highly diffusive. They naturally expand and untangle, losing their energy to the surrounding space, like ink dispersing in a glass of water. The solution lies in topology. If a continuous field line is tied into a complex knot, it creates a structure that cannot be unraveled without violently breaking its underlying geometry. This makes the field topologically protected. In the study of magnetohydrodynamics, this knottedness is measured as magnetic helicity. It is a strict mathematical metric of how field lines twist around their own axes and link together in three-dimensional space. The ultimate expression of this protection is the Hopfion, a 3-torus manifold. In this configuration, every single magnetic field line is a closed circle, and every pair of those circles is interlinked with one another exactly once. This creates a self-locking mechanism with a Hopf index of 1. While Diric's theorem suggested such 3D energy structures should collapse, mathematical proofs from the Vakulenko-Kapitansky bound show otherwise. Chiral interactions in the system favor continuous twisting, which pushes outward with enough force to perfectly counteract the tendency to collapse. The result is a Hopfion that neutralizes internal expansion pressure, providing a verified blueprint for absolute, self-contained plasma confinement. Bringing these shapes into reality means manipulating superheated plasmas. These fluids are notoriously unruly, thrashing and expanding violently when immense electrical energy is injected. However, observations from early experiments, like the Zeta machine in the UK, led to a discovery by physicist J.B. Taylor. Even the most chaotic, highly energized plasmas inherently seek a state of rest. This graph illustrates the mechanism of selective decay. Turbulent plasma rapidly burns off its excess kinetic energy through millions of microscopic reconnection events. But while the energy vanishes, the system's global topological knottedness, its helicity, decays much more slowly. The plasma slides down an energetic hill until it hits an absolute minimum energy floor, a state of calm born from chaos, known as a Taylor state. In this state, the system achieves a hydrodynamic equilibrium called a force-free field. The plasma organizes itself so precisely that the electric current flows exactly parallel to the twisted magnetic field lines. Because the current and the field are parallel, the cross product of these vectors is zero. This means the explosive outward Lorentz force effectively vanishes. Through Taylor relaxation, the plasma effectively builds its own invisible, frictionless cage, circumventing the classical limits of the virial theorem to stabilize itself.
Standard fusion reactors use violent, high-voltage sparks to ignite plasma, which creates immediate thermal stress and instability. Project Elyasia uses a more controlled chemical ignition. The fuel is a penning mixture of 99% helium and 1% argon. Helium possesses a metastable quantum state that allows it to hold energy without ionizing. This diagram shows the helium atoms acting like tightly coiled springs, storing 19.8 electron volts of potential energy. These metastable atoms bounce through the chamber, holding their energy until they collide with the sparse argon atoms. Argon has an ionization threshold of only 15.76 electron volts. During a physical collision, the helium atom transfers its stored energy to the argon atom, instantly ejecting an electron and triggering a clean, cascading ignition without high-voltage thermal shock. Once ignited, the plasma is shaped through coaxial helicity injection. Capacitors drive the plasma bubble outward until the magnetic field lines snap closed on themselves, much like a soap bubble detaching from a wand. This precise injection method traps the fluid within a closed 3 torus, creating the sustained Elyasia magnetic field without the violent shocks associated with pure hydrogen fuels. Sustaining this A-field cage requires a physical system with zero electrical resistance. If the hardware has even a fraction of resistance, energy will bleed out as heat and the topological cage will collapse. The reactor uses high-temperature superconducting toroidal modules, built from yttrium barium copper oxide, or YBCO. This second-generation tape features a superconducting layer only 1 micrometer thick, allowing it to carry massive currents without loss. When cooled with liquid nitrogen, YBCO's resistance drops to absolute zero. This allows the system to carry the immense electrical currents necessary to sustain the background potential field, even under magnetic loads exceeding 20 Tesla. Historically, these magnets were limited by their joints. Splicing the ends of the tape together introduced microscopic resistance that acted like a slow leak, eventually draining the stored energy. Project Elyasia utilizes a 2024 breakthrough, a jointless winding method. By using continuous unspliced conductors and thermal switching, the joint is eliminated entirely. By locking the A field within a zero-loss, jointless superconducting torus, the system fulfills the definition of a topological battery, storing pure energy in a non-radiating metastable state indefinitely. The ultimate objective of this architecture is to treat the stabilized A field as an interactive reservoir to manipulate the ground state of the universe. In quantum field theory, the vacuum is a chaotic sea of zero-point energy and microscopic fluctuations, already at its lowest possible energy state. Because it is passive, standard physical work cannot be extracted from it without adding energy first. However, the vacuum is linked by infinite quantum entanglement. The protocol for quantum energy teleportation, or QET, exploits this entanglement through local operations and classical communication. In the first step, Alice performs a localized quantum measurement on the field, injecting a specific amount of positive energy at point A. This thermodynamic downpayment disrupts the local field, generating specific correlation data about the quantum fluctuations. Alice immediately transmits this measurement data across a classical communication channel to Bob at point B. This transfer is limited by the speed of light, ensuring that the rules of thermodynamics and causality are strictly maintained. Bob uses this measurement data to apply a targeted quantum operation to his own local field. This allows him to mathematically squeeze the fluctuations, momentarily dropping the local energy density below the zero-point baseline. This drop below the 0 point creates a region of negative energy density, forcing the entangled vacuum to surrender positive, usable work to Bob. Because Alice already paid the energetic cost at point A, the global energy balance is perfectly preserved. This allows Bob to extract work without any physical particle traveling the distance between them. While QET has been demonstrated in microscopic quantum computers, scaling it requires an engineering platform that can maintain macroscopic quantum coherence. The jointless superconducting torus and the Taylor-relaxed plasma of Project Elyasia provide that exact environment. Together, they create a macroscopic quantum state, stable enough for the necessary information transfer protocols to survive. To interact with this state, researchers use MIMIM-shielded Borsch phase shifters. These devices use 5-layer metallic shielding to apply precise nanosecond voltage pulses to an electron beam, twisting its phase into specific geometric patterns without electrical crosstalk or beam deflection. These precise phase manipulations provide the physical interface required to act upon the field's entanglement. This allows the reactor to write data directly into the potential field. By integrating Aharonov-Bohm potentials, force-free plasma self-organization, and zero-loss containment, Project Elyasia moves beyond classical brute force. It establishes the verified groundwork for the topological battery and the dawn of vacuum energy extraction.